You all must have seen many airplanes flying in the sky, and you all must have thought that how do they fly. So let's study the basics of aerodynamics today. But for that, please do like, share, subscribe, and please support this video. And this video is purely mathematical. Okay. So suppose this is the runway. Okay. And suppose this is an airplane. Sorry, my drawing is not good. Okay. So suppose this is the wheels. Yeah. And suppose it is accelerating along this direction. Okay. So clearly it has wings, which I haven't shown. So let me show it like this. Okay. So what are the forces acting on this airplane? Well, there will be an mg force, and since it's on ground, so there will be a normal force N. Okay. And there will be a lift force L. Why do we get a lift force? Well, if you have ever seen the wings of airplane while takeoff, my drawing is not good, so I'll draw just a line over here. I'll show the real diagram in some time. Okay. So what happens is that this is the structure of the wings before takeoff, somewhat like this. Okay. Not exactly like this. I will show it properly. Okay. My drawing is not good, so I cannot draw. So what basically happens is that there's less hindrance for air to flow from the upward region of the wings than downward region. Due to which we know the Bernoulli's principle, P plus half rho v square plus, since they both are almost at same height, so we can neglect that term, is constant. Okay, we know this thing. So it means that pressure is some constant minus half rho v square. Since for the same amount of time, this the upward air is traveling more distance as compared to the lower the bottom air, right? Which means that if I name it as P bottom and this is P above A, then PB will be greater than PA. Understood? Why? Since velocity of B is less than velocity of A, since the air is traveling more distance in same amount of time as compared to the air which is moving in downward direction, I mean in the bottom area. Due to which the velocity will not be same in both the cases. So here velocity, suppose P of A will be K minus half rho V A square. So here V is greater than VB. So PB is K minus half rho VB square. Correct? So from here you can clearly see that if VB is small, then PB has to be a big value, a greater value as compared to PA, which will create a pressure difference delta P, PB minus PA, and hence an upward lift force PB minus PA times area, the surface area of the wing or the wings. Okay. So this is the lift force actually. So lift force is actually given as, well, let me erase this, then I will explain it further. Okay. Yeah, so lift force is given as half rho A CL V square, where rho is the density of air, A is the surface area, okay, of wings, and CL is the lift coefficient, okay, is the lift coefficient, and V is the velocity. Okay, V is the velocity. Okay, so clearly we can balance the forces over here. So we'll have N plus L is equal to mg because there's no vertical displacement right now. Okay, so I have erased forces along vertical axis and now I'm going to calculate the forces along horizontal axis. Okay, so what are the forces acting along the horizontal axis? For the vertical axis we had the equation N plus L is equal to mg. Okay, for the horizontal axis what will be the forces? Well, there will be a thrust force produced by the engines, and due to the motion there will be a drag force and there will be rolling friction. Okay, so if I balance the forces along horizontal axis, what I will get? I will get T minus D minus F is equal to ma, where m is the mass of airplane, of course. Okay, so we get T is equal to ma plus D plus F. Okay, and D is given as half rho a c d. This is the drag coefficient and the velocity square. Okay, so this is the thrust required over here. So this is the thrust at any moment. Okay, so N plus L is equal to mg and this is along the horizontal axis. Okay, so while takeoff, the normal will tend towards 0. Of course, the plane is slowly losing the contact with the ground, so normal of course tends towards 0, right? Okay. So we will have this equation N plus L is equal to mg. So N will tend towards 0. So we'll be left with L is equal to mg. This is the case, this is the minimum value of lift required. Okay, so when L minimum is equal to mg, at that particular moment the apparent weight of the airplane will be 0. Okay, so what is L minimum? How we calculate it? So L minimum is half rho ACL times the velocity minimum, the minimum velocity required for takeoff, right? If L will be greater than mg, then takeoff will happen, right? So this is the minimum, this is the limiting case actually for the lift force over here. So we will have half rho ACL V square should be greater than mg for takeoff, which means that velocity is greater than 2 mg by rho ACL. Okay, so the minimum velocity required is 2 mg divided by rho ACL. At this velocity, the apparent weight of the airplane will become 0, and if you give more lift to the plane, it will fly, it will take off, right? So this is the minimum velocity required for takeoff, right? And for the case of thrust, T is equal to ma plus D plus F. While takeoff, we can assume the acceleration to be approximately equal to 0, right? So if I assume acceleration tends towards 0, and since friction is somewhat proportional to the normal force, because we know friction is proportional to normal forces, so we had assumed since while takeoff n will tend towards 0, which means that friction will also tend towards 0. So we'll be left with T is equal to D, right, in case of takeoff. Okay, so this is how we calculate the minimum velocity for takeoff, and this is for the thrust force required. So if the minimum velocity is less than this velocity, or the thrust is not given in adequate amount, then the plane won't be able to take off or it may crash even, right? So this is how you calculate it. And let's take a practical example of an airplane which you all must have heard about. So let's calculate the minimum velocity required for that plane. You all must have heard about an airplane called as Airbus A380. and it was one of the largest passenger plane, if you know it. So let's calculate the minimum velocity required for takeoff for that plane. Airbus A380. So I have got the data for its mass. Its mass is approximately said to be as 5.75 into 10 raised to the power 5 kg. Okay, and area of the wings sorry, is given as 845 meter cube, and the density of air is assumed as 1.2 kg per meter cube, and the coefficient of lift with flaps is 1.5. Okay, so we had got the expression that velocity minimum, it should be square root of 2 mg rho acl. Okay, so just substitute the value, and when you substitute you get it around 80 meter per second. So the minimum velocity is 80 meter per second, which is approximately 280 kilometer per hour. And if you know the practical value is around 260 to 300 kilometer per hour, and that is really very accurate. Okay, of course there is a variation, because the density of air is not constant always. It is not always 1.2. Sometimes due to excessive heat the density can become less, or due to the presence of humidity or some other conditions the density will keep on varying. And of course if density will vary, so V minimum will also vary. Okay, so this is so this is how you calculate the V minimum velocity, and it's a very basic mathematics of how airplanes fly. I mean how they take off. So I hope so that you enjoyed this video. If you did, then please do like, share, subscribe, and please support this video. Bye bye. Take care.